Hi everyone, today I'm taking a look at this complex numbers question where we're told a quadratic equation with positive real coefficients has complex roots alpha and beta. The value of arg alpha plus arg beta could be, and then we've got these four options a, b, c, d, being pi, pi on 2, 0, and 3 pi on 2. So yeah, let's work through and see what we get. So if I write up our quadratic equation, so in generic form it would be ax squared plus bx plus c equals 0. And we know that a, b, and c are real numbers because we're told the equation has real coefficients. So we know this quadratic equation has roots alpha and beta. And we know that alpha and beta are complex numbers. We're told that the roots are complex, so we can write each of these in complex form. So maybe what I'll do is I'll let alpha be equal to x plus iy, where x and y are real numbers and I is the imaginary number. And let's let beta equal m plus in. And again, m and n would be real here, and we've got I as the imaginary number. So if we use our sum and product of roots rules, we know that the sum of the roots, alpha plus beta, would be equal to negative b on a. And we also know that the product of the roots, alpha beta, would be equal to c on a. So I think we can make use of these results by substituting in our alpha and beta, and then using a very common technique with complex numbers being equating real and imaginary parts. I think we're going to get to a place where we can work out the arguments of alpha and beta. So let's start with the sum of the roots. So if I just add up our alpha and beta, so we'll have x plus iy plus m plus in, so that's alpha plus beta, will be equal to negative b on a. And now I'm just going to bring the real and imaginary parts together. So we'll have x plus m plus y plus ni will be equal to negative b on a. And remember, b and a are both real numbers because all our coefficients were real. So if I want to write this in complex form, I can say it's negative b on a plus 0i. Or in other words, I've got no imaginary part, or 0 times the imaginary number. So now what I can do is I can equate real and imaginary parts, and what's really going to be helpful is the imaginary parts, because I've got 0 on the right hand side, so I can say therefore y plus n will be equal to 0. So n would be equal to negative y. So I think that's going to help us. We'll leave that there for now, and let's now take a look at the product of the roots. So if I took alpha times beta, I'd get x plus iy times m plus in would be equal to c on a. Now if I expand this out, I'd get x m plus x n I plus y m I plus I squared y n would be equal to c on a. Now if I bring the real parts together, this I squared is going to become negative 1. So we'll get x m minus y n plus x n plus y m I would be equal to c on a. And again, c and a are real numbers, so if I want to write this in complex form, it would be plus 0i, just like I did up here. And again, if I equate real and imaginary parts, focusing on the imaginary parts, I can therefore conclude that x n plus y m is equal to 0. So that means x n would be equal to negative y m. Now remembering that n is negative y, I can substitute that negative y in here, so I could get negative xy is equal to negative ym, and this kind of the two negatives will cancel and the y's will cancel, so that we end up with x being equal to m. Now if we think about those two results, we can actually come in and kind of rewrite our alpha and beta in a way that makes it really clear what the arguments are going to look like. So I might just turn over, create a new page. So we're going to say alpha is equal to, we had x plus iy, noting that, actually let's just leave that. So we'll have alpha is x plus iy, that's fine, that's how we defined it. Now beta we defined as m plus in, but m we've concluded is x. So let's just, instead of writing m, we can write x. And we had plus in, but n is equal to negative y. So instead of saying plus in, I could say minus iy. So let's come back and write minus iy. And now we can see that alpha and beta are actually complex conjugates, because it's basically something plus I something and something minus I something, where the real and imaginary parts are the same but for this negative. So if I was to say draw this up in an Argand plane, if I just sketch up an Argand plane very quickly. So if we had our real and imaginary parts and I wanted to plot alpha and beta, I'd come across some value x and then come up some value y, and then the actual point there would be alpha. And if I came across the same value x and down the same value negative y, I'd get beta. I'll just erase these to clean it up a bit. So we've got our alpha and beta being the same distance across and the same distance up and down. So that if this angle was some amount theta, then what I'd know is that this angle would be the same magnitude, just the negative version of it. And therefore, we can conclude that the argument of alpha plus the argument of beta would be equal to, well, this angle here is the argument of alpha, which I've just defined as theta here. And this angle here is the argument of beta, which is negative theta. So we get theta minus theta, which is equal to 0. And that option there was option C. Panic boom! So the answer to this question is C. And yeah, that's all there is to it, really. Hopefully you're able to follow along with all that. I think this is just one of those classic quadratic and complex number questions where you're making use of your sum and product of roots formulas, which you would have learned quite a while ago in the context of doing an Extension 2 exam. But you're then combining that with a technique that hopefully you'll be very comfortable with, which is the idea of equating real and imaginary parts. It's something that you'll do over and over again in lots of different kinds of questions. And here, particularly focusing on the imaginary parts, we've been able to get some results that allowed us to get to the point where we've got complex conjugates, which then lets us realize that the sum of the arguments must be 0. So yeah, there you have it for that question, and tick boom.